Yes, good morning. Please go ahead, Alan.
Good morning, everybody. My name is Alan Geary, and it's my pleasure to address the subject of the history of civil engineering and the implications that it has for inspecting existing buildings. So what we're going to be looking at is the seven basic ages of civil engineering and their legacy for how structures behave and the implications for a person who's doing an inspection of a building. Now, modern civil engineering has looked at various different stages. I've produced 7 of them, which I think are important for the structural changes which occurred as as a result of that. And so we'll look in particular detail at the post-industrial revolution type of structures that we're dealing with. We'll look at the causes of collapses, and particularly we'll look at the way that codes of practice have changed in the last 100 years, and particularly the change to performance and risk assessment. We'll talk about moving from a static assessment to designs that to changes that affect the risk of a structure undergoing some sort of a problem. What risk is acceptable for wind, earthquake, and flood occurrences? And particularly, we'll look at the statistical approach, indications for a localized problem in a building and what to look for, and then indications for an overall, a holistic assessment of an entire building and how to perform that. And then generally about building inspections, what we should look for. So first of all, let's start with these 7 ages of civil engineering and their legacy. And these are the basic ones. And I'm going to go into a little bit of detail here. Essentially, we start off with early civilizations between 10,000 and 500 BCE. And that essentially occurred looking at palaces, burial tombs, ziggurats, pyramids, great walls of China, and to keep out enemies of particular civilizations. Then we have the classical antiquity, which is between 500 BCE and 500 CE. And that's basically the Greek and Roman civilizations. They introduced codification of sorts, and they were particularly interested in producing roads to transport people, food, and various other things around. But particularly, they were interested in the water supply. The Romans, particularly, developed concrete in their early stages, and the Chinese produced the roof tiles during that period. In the Middle Ages, from 500 CE to 1500 CE, there were again castles, Gothic cathedrals, windmills, and a lot of water management, which happened largely in the Middle East. This was a time when Gothic architecture had its original occurrence, and that occurred between the Middle Ages and the Renaissance. Some people will say that the Gothic period and the Renaissance were in parallel, but in fact they're very different in time. From Renaissance, we had a very large change in civil engineering. We had some of those people that we regard as very important to civil engineering. So we had Galileo, Hooke, and we introduced surveying instruments during that time. Then along came the Industrial Revolution, which was from 1760 up till 1900, in which science had a large part to play. Materials were changing, iron and steel were used. We developed railways, we developed urban infrastructure, and reinforced concrete. Then the sixth age is the early modern approach from 1900 to 1999 CE. And there we introduced elevators, which allowed us to build taller. We had steel, which we used for structures as well. We actually revolutionized our codes and our standards at this time as well. But probably of more importance to us was the electronics revolution. And that has made a big difference to what we can do in the last age, the modern age, 2000 to date, where we have things like high technology, artificial intelligence, automation, advanced materials, and sustainable design. So let's look at these in turn, and I'll have a few pictures so that you can gain some idea of what our buildings looked like in that time. So this is the very earliest stage there in Pakistan, which were mud-built homes, and that's one at Mehrgarh in Pakistan, about 7000 BCE. Then we have Cairn de Bananaise in Finistère in France, which was about 4850 BCE, and it's known as the prehistoric Parthenon. I'd like you to notice here that the materials used were stones, and these were fitted together. It was a type of building that we went on to use for over 1,000 years. This is in the Nap of Howar in Scotland, where the climate was quite challenging. And you can see that, again, we have a number of stones put together by people who knew what they were doing, what they wanted to achieve, and they sheltered inside these small houses. And then 3250 BCE, there is a temple in Malta. And in fact, during all of this period, we found that the people who were in charge, the ones who manipulated civilizations, wanted cathedrals, temples, various things, and forts to be able to protect themselves. And this was in Malta. And then you're probably aware of what was going on in Egypt. This is 2670 BCE, and it's actually the first of the pyramids that they constructed there. And it's the Pyramid of Djoser in Sagarat in Egypt, and of course the Great Pyramid of Giza, which you're probably more aware of, and that was built 2560 BCE. In Syria, we had remains of the Zimri Lim Palace there. Again, you could only build something extensive if you were a person of great power. And you can see again here, this is basically mud, which is held together and cracks quite easily as well. And then we move into 700 BCE, in which there are um, uh, um, uh, properties which are called necropolises. This is burial chambers for important people. And then we move to between 2000 and 1300 with the Greek civilization. Again, you can see we had large rocks. Now they were cut in a better form, easier to put together, making a more stable type of structure. Although you can see in this wall here, there was this loose arrangement of stones as well. Now we were building, though, pillars which were supporting roofs. And then classical antiquity, 500 BC to 500 CE. And there, of course, we have the Parthenon in Greece. Now, this was now a much more extensive structure. It looks as though it underwent a lot of problems here, but it didn't. Ammunition was held in there for a long time and exploded, causing the problems, and has never been put right. The Romans invented cement, and they put together those building blocks and held them together with cement. There was a deficit of thousands, 1500 years, in which no progress was made after what the Romans achieved. But the Romans did incredible things. These two structures were from the Roman ambience. There you can see the Parthenon, the dome, and the Segovia aqueduct. Now, they were very, very clever in getting water to come into their industrial areas. And these Segovia aqueduct was used for over 1,000 years afterwards. This is the Parthenon, and you can see the dome in the background there, and that's a view from outside. And another Roman aqueduct there in the Pont du Gard in France. Actually, this one just recently has had an extra roadway built here, and it's used extensively. In fact, just yesterday, the Tour de France went across there. And this is the Segovia aqueduct. You can see the use of arches, but very little cement in there. You can see, if you look closely here, that the stones were applied very carefully so that gravity would hold them together. And the use of the arch principle was extensive in Roman times. They were also very good throughout Middle East and Southern Europe in looking at the use of water for people bathing, cooling, and various things. Now, at this time, the Qanats underneath the Persian desert was built in 700 BCE. Now, remember, at that sort of time, there was no electricity, There were no hand tools. These were hand carved and were built with such precision that the water would flow usefully, and people could go there to bathe. In this particular view, there is a Roman city gate. It is the Porta Nigra, and you can see if you look very carefully that the building blocks are now held together by cement. And so these have lasted a long time. In fact, they've lasted over 2,000 years. Now we come to the Middle Ages, and we have Machu Picchu, which was built in the 1400s. And you can see in here the rocks were placed together. They were produced so they had a particular form that was useful for maintaining stability. And there was no cement in that particular case. And then if we go to Faroe Islands, long way north in Europe, and what we have there is a classic style of building with wood. But you can see that the roofs were grassed. In some cases, they had hay, so that the rain would not go in there, and the influence of China, where they had produced roofing tiles to prevent rain from coming in, had not reached Europe. Then we have something very interesting occurring. Again, it was a religious organization that wanted this sort of thing. What they wanted was very thin walls, very tall walls, with lots of windows to them as well. But the early attempts at building structures like this fell down. So what they did was to put these devices on the side, and they're there to create stability of the wall itself. You can see with these little X pieces as well that there is an added stiffness to go in there as well. So these things are called flying buttresses, and the buttresses perform a lateral stability so that the incoming forces of whatever, the wind and whatever, would not overturn the building and cause the wall to fall down. Then we had more from 1500 onwards. There's the St. Peter's Basilica in Vatican City, which was built in 1626 CE. And again, you can see a large dome there, which is not completed there. There's something on the top because the bit that comes close to being horizontal for a dome is difficult to maintain stability. We also had Villa La Rotonda at Vicenza in Italy, 1567 CE. Again, there's a large dome there to allow a large meeting area inside the structure. But once again, you will see that stones have been arranged and they are held together by rudimentary cement. And then we had 1635. I've got into some detail here because it's a watershed as far as civil engineering is concerned. Robert Hooke was son of a pastor. He lived in poverty in his youth, but he was clever. And so he, with very little money available to him, he became an apprentice. He went to Oxford University, worked with Boyle, and he was asked to help with the reconstruction of London after the Great Fire of 1666. Now, at that stage, he and several other people founded an organization called the Royal Society. They did this because they were interested in entering science into the general ambience of the way that people did things. Hooke himself was intelligent. He inferred a number of things. For instance, the wave theory of light, the gravitational square law, which revolutionized astronomy later on, that air was composed of very small particles. The theory of biological evolution was his. But the big one that we in civil engineering are interested in is his law of tensio sic vis, which means the extension is proportional to the force. It was a time of denigration of science, so the Royal Society moved that around and put science into a dominant position in what we did in civil engineering generally. The Royal Society attracted a number of people who wanted to have the scientific ideas into the mainstream of society. Now, the Royal Society was formed in 1660, and to date, there are only 26,000 people who have been accepted into the Royal Society. There are no exams. You have to be at a very high level in engineering or scientific institutions before you are invited to be a member. So some of these members are Isaac Newton, Albert Einstein, Thomas Young, Robert Hooke, Benjamin Franklin, Michael Faraday, Charles Darwin, Paul Dirac, Winston Churchill, and Stephen Hawking. And I myself am a member of the Royal Society as well. We use what those people did. So we have Newton's laws of motion, Young's modulus, and Hooke's law, all of which have revolutionized what we do in civil engineering. Now, if we go to college, then we do very simple experiments, which are actually looking at Hooke's law and Young's modulus. So, in other words, if we have a spring and we have a weight on it, then it extends by a certain amount. If we have 2 times that weight, then we have 2 times the extension. So Young's modulus will tell us what that can be. Newton's second law of motion, force equals mass times acceleration, we also use to some extent. So just look for a moment commonly used equations in civil engineering. Firstly, the ratio of stress to strain. Sigma is stress and epsilon is strain. So E equals sigma upon epsilon. That is E, the Young's modulus. For a bar with a constant cross section and deformation, then we have the deformation is F, the force, L, the length, upon A, the area, and E, Young's modulus. Deflection of the beam, simply supported, and the central point load, then delta, the deflection, is P, the force, L cubed, the length of the beam, upon 48 E, the Young's modulus, and I, the moment of inertia. Critical buckling load, PCR, of a column of length L, a moment of inertia I, is PCR equals pi squared EI upon L squared. Again, we have Young's modulus there. So Hooke and Young absolutely revolutionized what we are doing these days. If you are if you've been to university or college, then you will undoubtedly have undertaken some of these laboratory tests in which a load is applied to a beam and we measure displacement in some way. And we use devices for creating larger forces, and we're using the Hooke's law, which says that the displacement is the force divided by the stiffness. Everyone does this type of testing when they're at school. Now let's just leave that for a moment and we'll come back to it and take you on into the Industrial Revolution from 1760 to 1900. This was also a time of the Enlightenment where science actually got a dominant position as far as engineering and civil engineering occurred. So the Industrial Revolution was based on the use of coal. It was the use of fossil fuels. We weren't so worried about the environment of the earth in those days. What we were interested in was creating heat, thereby steam, and being able to manipulate all sorts of things. We were also able to create iron because we could have blast furnaces in which we created the iron. And this is a picture of the Iron Bridge in Staffordshire in the United Kingdom. It was built from 1777, 1779, and it was the first use of iron to create part of a bridge, a part of a roadway going via a bridge over a river. At the same time, in North America, this around the same time in New York City is Castle Clinton. There were defenses necessary on the southern end of Manhattan, and you could see that actually what was occurring there was large blocks placed on top of one another, and they are very large as well. So again, it was gravity which was creating the stability of this particular structure. If you look in New York City and other places in the United States around that 18th century earlier, you'll see that the use of brickwork was very haphazard, but there was rudimentary cement type. So in other words, if you have a building which is that old, be aware that the cement is going to be less stable. Then we come to the early modern period, in which 1900 to 1999, we looked at, it was a period where we started looking at the dynamics of structures. We had unusual structures as well because science was extending and allowed us to do all sorts of things which we hadn't been able to do before. And there is the Sydney Opera House, which was commenced in 1959 and was opened by Queen Elizabeth in 1973. This is the Hubert Humphrey building in Washington, D.C., which was built in 1977. Now, during this time, we were aware that we had to resist the forces of nature. And our approach very definitely was to produce buildings which were large enough and stable enough to withstand those forces. We didn't have enough expertise to produce that to a large extent. This in 2004 went on to the Seattle Central Library, and that is somewhat unusual, but it allows you to see the structure itself. The architect wanted you to see what the structure was doing in this particular case, and look at that in comparison with the buildings which are around, in which the large columns and various pieces of the building were load carrying. This is the Nakagin capsule tower in Tokyo, and it was built in 1972 CE. The idea was that each of these capsules could be taken away and replaced with something else. They never have been. It was too much effort. But then suddenly there was a problem. Dynamics was involved. What happened here was the Tacoma Narrows. So, in other words, what happened was that the bridge itself, just 3 months after it was built, collapsed. And it collapsed because the excitation from the wind caused vortices to form, and the vortices forced the bridge up and down. And there is a critical wind velocity which produces a vortex at the resonance frequency of the structure. So the structure itself had a resonance which would allow it to move upwards and downwards, and the vortices occurred at a particular wind speed, and that created this problem of destruction. Have we learned from it? No, we haven't. This is the RFK Bridge in New York City, in which, in this particular case, we are monitoring damping. I'll come back to that later, but damping would normally be this level and then rising as the amplitude of response increases. But what we've got is two areas here where we have excitation that forces the structure into larger amplitudes of response. In other words, it's vortex excitation in exactly the same way as there was a problem with the Tacoma Narrows. However, in this particular case, the wind speed which causes that resonance is so high that it is not a problem for the RFK bridge. That's because the RFK bridge has a fundamental natural frequency of approximately 0.2 hertz. In other words, one cycle every 5 seconds. So the critical wind speed is too high for it to be a problem. We also had the Ferrybridge cooling towers. Now, a group of 8 here, the wind was blowing from the north, and it produced a vortex between these upstream cooling towers and blew down with increased forces, blew down these 3 towers here. The question is, why didn't this one fall down? And all I can tell you is it probably was going to be the next one that occurs. I spent some time on site at Ferrybridge, and they met somebody who'd actually been involved with the construction there, and I made a comment to him saying they should have been 10 inches thick. They shouldn't have blown down. And he said they weren't 10 inches thick. I built them. They were 8 inches thick as a maximum. And so the stiffness of the cooling tower was not enough to negate the effort of the wind. However, we didn't at that time in 1965 understand what the dynamics of the response of cooling towers is, and they are very, very complex. We have problems of scour, and then we had gas explosions. This building is Ronan Point in the United Kingdom. It's in London. And in fact, 4 stories from the top, a lady woke up early, went to her kitchen, switched on the gas and the whole thing exploded. What happened then was that the roof went upwards and took out the apartment above, and that took out the apartment below that, above that, and then all of them took out those below them. Now, why am I so interested in something in London, in the UK? Well, actually, for two reasons. First of all, Ronan Point is actually in ASC 7. The things that we learnt from progressive collapses on this building, Ronan Point, are still valid today. The second thing is that we did a test, an induced vibration test. I say I did. I shook this building to find out exactly what was happening to it. And in practice, it was coming apart at the seams. It was not very well constructed either. So the British government decided that we should not allow such a building to be built again. In fact, in the United States, this type of building, the Larsen-Nielsen system, which is large panel construction, was allowed only up to 5 stories. In the United Kingdom, it went up to 24 stories. So we built in our laboratory a model of this building, 24 stories tall, at 1/4 scale. So you can see it was an extensive device. However, we put in loading, which looked like a gas explosion, and we got a progressive collapse there. Now, this is interesting as well, because what happens when a government has gone in, they've had a problem, and they've altered the law to say that you must build in a different way now, so that this will never happen again. So what we produced in our laboratory was something just saying, sorry, it's going to happen again. It just needs the force to be larger than that. And they refused to allow us to publish it as well. So you're all asked to keep this quiet. There were other things going on. Teton Dam failure, which was in the US. But what was happening? We were actually deciding that structural integrity is a must of structures. With Ronan Point, we decided that we had to define how we were going to affect construction. And that's come into codes of practice, including the United States ones as well. So the codes allow for testing of structures, but currently engineers cannot verify structural integrity as required without measurement. So I'd like to step back again to say, okay, let's look at the process of design of structures. What actually do we have to do to do that? What do we give to an architect, a builder, to decide exactly what's going to be necessary to construct the building? First of all, we obtain a record of large forces and their magnitudes which occurred. Secondly, we analyze these for the average return period for different intensity events. So you'll see the two diagrams that I have below are on the left earthquakes and on the right winds. Now what we have on the left is the intensity of earthquake that gives a 1% chance of collapse of a structure in a 50-year period. On the right, we have wind, 3-second gusts that will occur on average at least once in a 50-year interval. Now, those lines are of equal wind speed. They are called isotachs. On the left, the earthquakes, they are equal intensity of earthquake, and they are isopleths. Now, all it means is that along that line, the maximum speed that you're going to get for a wind, maximum intensity for an earthquake, is going to be the same. Not actually the same, but the probability of them occurring is the same. For wind, it gets more analytical in that we must look at directionality as well. And for earthquakes, we must look at the difference in soil conditions. So we've produced a map, a localized map for different geographical areas. And we look at probability of occurrence. And of course, we don't have the ability to look in every single place that are going to be of interest to us. For sparse data, if we have only a short length of record, then we can use something called the Lieblein Blue estimator. Best linear, unbiased evidence of a wind. Now, imagine that we are looking for a once in 50-year wind. Have we got 50 years worth of data? Well, yes, we might have something like 70 years if we're lucky. In some places, they only have 20 or 30 years. But if we have a period of time that only estimates once in 50 average from a data set which is 50 or 70 years long, then we're pushing statistics to the limit. So we take, in the case of wind, we take the average or the normal value, and then we look at how that equates to the extreme that will occur. And the extremes and classical normal statistics will tell you what the mean value of wind will be. And we'll look at that in a little bit more detail later. So the problem is that the ratio of the extreme to the mean is not always constant. This is something produced by a colleague of mine, John Bain, at the Building Research Establishment. On the right-hand side here, we have, and red dots represent a once in 50-year event. There are, of course, 100 of them, but it's a random process. So they don't occur once every 50 years, they occur at random intervals. Sometimes you get none, sometimes 1, 2, 3, even 4 in a 50-year period. That's all assuming that it's a random process only. If we were unlucky enough to have climate change as well, then the whole bottom of this chart would be filled with red dots. Let's assume for a moment that there is no climate change, and what we have is the probability is governed by this equation. P equals 1 minus 1 upon S to the power n. And what we have there is P is the probability, S is the return period, and n is the number of years. So if we take a 50-year period, then we have 1 upon S is 1 upon 50. That's 0.02. That's 0.998 raised to the power. N is the number of years. So if you raise it to 50 years, you'll find that the probability of occurrence of 50-year wind speed in a 50-year period is only 63.58%. That's what statistics will do for you. So now we have to look at structural integrity and see what we're actually dealing with. We're going into a building and we're going to try to assess whether it's stable, whether it has structural integrity has changed over the years. Firstly, it evolves from structural adequacy, and section 1.4 of ASC 7 provides detail and quotes Ronan Point that I've just mentioned to you. The ability of an entire structure and its elements to carry an imposed load without distress is structural integrity. The imposed loads are those expected in the design process. So we need to know what the design process is playing with. The expected loads are risk-based, as I've just explained. Distress is a function of the type of loading. Essentially, there are three types of loading satisfying the following criteria. Number one is human comfort. Never mind the structure, human beings have to be comfortable to work inside structures, and human beings are the most sensitive aspect of looking at structural integrity. Second area is the linear elastic behavior of a structure. And the third area is collapse avoidance. So basically, inside wind engineering, we look at linear elastic behavior, and we don't want the structure to go outside that elastic behavior area, at least not often anyway. Earthquake, we want to avoid collapse, and that means that we will be outside the linear elastic behavior, and the structure will undergo some sort of cracking, and ductility will be used. So long as it doesn't collapse, that's what the design will look at. Let's come on to the modern era, because now we have high tech, we have the electronic revolution, we have drains, automated design, 3D printing, advanced materials, and of course, a lot of mathematics that help us as well. So let's just take a step back for a moment with the electronic revolution. The vacuum tube was invented by excuse me, invented by Fleming in 1904, and this was a vacuum tube so that electrons can move in a deterministic way. They were difficult to use. The transistor was invented in 1947. Transistor meant transfer resistance. Essentially, a transistor allows a variable resistance. So in other words, if the resistance is very high, no current will flow through. If it's very low, all the current flows through. There we have it, a 0 and a 1, which is why we have digital technology. And then, of course, if we look and put a lot of transistors together, we have integrated circuits. They were invented originally in 1958, and that allowed the miniaturization of transistors, and that allows electronic systems which allow us to have large-scale computers, supercomputers, quantum computers, electronic measurement, artificial intelligence, organic electronics. In fact, the electronic revolution is going through a new stage of increasing these days, so that we're getting a lot. We're seeing it these days with artificial intelligence. And that has allowed us to produce the type of building which is quite different from what the Romans did. This is Fukuoka in Japan, and this is a modern building actually in this country. So now, of course, we know better. Do we? No, we don't. There's a series of problems. So let's just look about things vibrating. Everything vibrates. The absence of motion is almost impossible. Theoretically, it can only happen at an absolute zero of temperature. So, in other words, everything is in motion all the time. Some things vibrate a lot. We design structures to withstand forces of excitation, such as wind, flood, earthquake, and a number of others as well. But consider every cell in a human's body also vibrates. So do parts of the body. The stomach, for instance, vibrates, which is why you shouldn't follow your children onto um, devices for creating large vibrations, because your stomach is a different size to theirs, and you will suffer more than they do. So an acceptable vibration is when it doesn't do a damage to a structure. What causes damage? Well, firstly, as far as structures are concerned, then it's because the stresses become so large that they rupture elements. There are structural and non-structural elements to consider. The initial signs of structural distress occur in non-structural elements, and at greater amplitudes, the stresses are large enough to cause rupturing of elements of the structure itself. But what about human comfort? And this depends very much on individuals. We're all individuals, we all behave in a different way. So are we uncomfortable? It's dependent on our posture, on what we're doing, and your experience of what you know of vibrations in the past. So the lowest form of response is that loose objects will rattle. At certain frequencies, some organs in the body resonate. That's why we walk comfortably at about 2 cycles per second, because the organs that we have inside our body are resistant to those frequencies. It's comfortable for us. At increased amplitudes, a person feels nauseated. That's called kinetosis. So that may well be that your stomach is vibrating, so you don't want its contents anymore. An even greater amplitude, people assume that the structure is in danger and they will run outside, at which time, of course, the greatest risk is from items falling off a structure or blown through the air. Moving on, vibrations themselves travel through solids and through amorphous bodies like air and water. Vibrations travel at different speeds through different types of body. If the vibrations travel through air, they're perceived as sounds. And if we do a spectrum analysis, we use a totally different estimate of what a human's perception of a sound will be to what a structure's perception of vibration will be. As a result, sound intensity is measured on the decibel scale. Small d, big B. The big B is because the unit is the bell. Deci means 1/10. So dB is sound intensity. Vibration, on the other hand, rather than sound, is measured using acceleration or velocity. So what about human intensity then? The human sensitivity. So what we have is a number of different levels of excitation by vibration that will cause a different response to humans. So number one is vibration is just perceptible by humans. That would be at 0.007 inches per second. Now, if we assume that that's times one and see what the rest is. Second level, people become uncomfortable. That's 10 times larger at 0.07 inches per second. Third one, people get highly distressed, and that's at 0.67 inches per second, approximately 100 times. So, in other words, 100 times the the perception level will just take you to something that you think, I do not want to be here. However, you go up 700 to 745 times before light cracking in non-structural elements occurs. Damage to non-structural elements at 10 inches per second, 1490 times. Structural failure we get 17 inches per second, 2537 times the threshold of perception by a human being. And then 30 inches per second, the destruction of a structure may start to occur anyway. So that's the effect of a vibration on humans and on structures. And here we have a graph showing that. So we have human response zone, which is threshold, discomfort, distress, and then here we have the structural zone going up to level 7 there. But you can see that it's a sort of exponential rise there, and that's the vibration intensity multiplication factor which occurs. So, in other words, what I'm trying to impress on you is that if you're inspecting a structure and people are complaining that the structure is moving, then they are going to be in this lower area here, even if they're in distress over what's happening, then they may not be a good indicator of whether the structure is in difficulties. Like cracks, okay. So we need to be looking for cracks, and we need to be seeing whether those cracks are occurring as light cracks or whether they occur as damage in structural elements. So we move from level 4 to level 5 here. And structural failure, we still got a lot of room for something to happen before a structure will be in a lot of trouble falling down. There is also a need for a structure to dissipate energy. And the parameter which defines energy dissipation is damping. We have here two examples, one of 4% damping and one of 1% damping. Now, the thing is that a structure will have probably between 1 and 2% of damping. If it has a higher amount of damping, it's because the energy is being lost somewhere. So just have a look at this. On the right-hand side here, we have a structure which has very little damping. And on the left-hand side here, we have the same structure, but now it has damping. In other words, energy is dissipated into the tablecloth on that table. So if I set it going, that's the low amplitude, and there is the high amplitude. and you can see that high amplitude will stop the structure from vibrating much quicker than a low amplitude damping, low damping ratio. So damping is very important. It allows you to define what the maximum response of a building is going to be. You might say, well, we actually want higher damping then. But no, we don't, because higher damping is caused by energy dissipation. And you know, the main reason that energy gets dissipated is through cracks in the building. And when there is differential movement going on, then the crack is elongated as well. So, yes and no. A larger amount of damping is an indication that there may well be damage inside the structure. We'll come back to that. And then, of course, we had something which set us into panic. The Champlain Tower in Florida, part of the building collapsed, and we had a lot of discussion of what caused it. NIST still hasn't produced their report about it. And during this time, there were various things that were occurring. There was deferred maintenance, funds not used to address damage, repairs, which they knew they needed. In 2018, that was estimated as $6 million. In 2020, it was estimated as $15 million. And then June the 24th in 2021, the structure collapsed and the repairs had not yet been started. Property manager knew of the weaknesses. However, Florida decided this must not happen. So Florida changed the law in Florida. A number of states in the US followed suit. And what they did was to say you must assess a building for structural integrity, and you must also have a reserve so that once the structural integrity result comes in, then you have a a rationale for what you're going to do for maintenance on the structure, and the money that you've set out must be adequate for doing that. Unfortunately, that's running into trouble, and a lot of people are just simply leaving buildings like this, and they're going off to live somewhere else, which leaves the owners of the building with a big problem. We also had something in Davenport, Iowa, which is a 100-year-old building, and a large amount of the external wall was demolished. 3 people died in that, and more, though. 70 families were left homeless. The the structure had documented deterioration, but nothing was done about it. And in fact, in 2020, there was a Derecho, which is a wind form in which a long line of vortices occur. And basically, the speed was 126 miles per hour. Florida passed Senate Law 154. And I want to read you something that is in that law. The legislature finds that maintaining the structural integrity of a building throughout the life of the building, its service life, is of paramount importance in order to ensure that buildings are structurally sound. So, what do we have to do? An inspection has to be performed under the direction of an architect or engineer licensed in the state of Florida for the purpose of attesting to life safety, the adequacy of the structural components of the building, the general structural condition of the building as it affects safety of the building, including safety, repair, and replacement. They also have in there a statement that it is to the extent reasonably possible. You can bet that there's going to be a lot of lawyers arguing about that. Now, the point of this, though, first of all, what they've done is to say life safety. Okay, we don't want human beings to be accommodated largely. They must be comfortable. Secondly, there must be the adequacy of structural components. Now, if you go in to do an inspection, you're going to take a look and see if you can see structural components which are not in a good state. Okay. The third is the general structural condition of the building as it affects the safety of the building. Now, how do you assess that if you can't see? If there are parts of a building which are behind panels, things like that, it's impossible to tell. So you must have a different form of being able to measure, and you do have it. It is possible to do a third level, which is holistic. Cause of collapses, well, first of all, the incoming force is not channeled to the ground. Foundation is not strong enough to take the imposed load. Load path includes an area that's insufficient for the imposed load. Horizontal capacity is insufficient for the imposed demand. Vertical capacity is insufficient for the imposed demand, and the imposed force is greater than assumed in the design. So now we come back to this. We now have the design assumes a force, and we will have the response of a building which is okay as far as human occupants is concerned, the structure itself is concerned. Again, we have this three levels: human comfort, structure being not not particularly badly affected, and thirdly, it doesn't collapse. So the modes of failure. This is an interesting one. Mode of failure must develop if the structure is no longer capable of performing as intended. In other words, what that's saying is that human beings must be comfortable in the structure. Human response is the most complex type of failure as well. So physically, elements can no longer take the intended loads and parts of the structure begin to act independently. So in other words, if the cracks are large enough that they make little parts of the structure independent from other parts, then you've got a failure, which is important. And here are some in history. We have the Mara building over there, which was a bomb blast. We have a gas explosion there. We have the Statue of Rhodes. We have the Ferrybridge cooling tower. We have terrorism there, the World Trade Center in Manhattan. That occurred in Japan, where the foundation failed and the whole building came down as one element independently. This occurred in France, an ordinary device in which the loading on the floors was too great, and there an explosion which occurred. And there's a list of them which you can see in them, but I do want to point out here that there are a number of items which occur, and they occurred throughout history, and we need to be aware of them. First, the Tay Bridge in Dundee, Scotland. That allowed the bridge to collapse a train was deposited in the water. So we changed regulations. At that time, we were assessing a wind loading force as 10 pounds per square foot. So easy. We increased it from 10 up to 20 and later up to 30. Roland Point in 1968, a gas explosion, 4 deaths, but we knew then about disproportionate response, a progressive collapse. So we changed the building regulations so that we would avoid that again. I've told you what happened with that. It was inconvenient for the government, so they wouldn't allow people to have a look at it. Then there was a building in Bangladesh. In this case, there were 1,300 people who were killed. The Spectrum factory collapsed. And 8 years previously, they had heard cracking in the building. They'd changed regulations, but nothing was done about this. In fact, in that particular case, on the day that it happened, people heard large amounts of cracking occurring in the structure. And then there's Magnitogorsk building collapsed, 10 stories tall in 2018. 2018 in Russia, there was a gas explosion. So look at this. This is Roland Point, 1986, and the same type of progressive collapse occurred in 2018. So we've got, what's that, 50 years afterwards, and 39 people killed as a result. And then, of course, the Champlain Tower. So we know what to do. We'll change the regulations. No, we need to do more than that. We need to do a lot more than that. And part of what I'm trying to tell you is how to do a lot more. So during the last 100 years, we've changed our codes of practice. And we have moved from this idea of a quasi-static force that we designed for. And we then moved to performance of the structure and a risk assessment. And of course, we still have design errors, but this is what we did with the codes of practice. In 1879, there was the Tay Bridge disaster. We had the Tacoma Narrows Bridge failure. In 1950s, we were still using prescriptive design. In other words, we would say what size columns need to be, how thick floors need to be, how far apart we would put columns. And we took a long time to realize that that isn't really what we want. In 1989, we're moving towards goals. In other words, never mind saying that you must build with certain size columns, you must actually achieve some sort of goal. So we started doing that in 1989, and that effectively was the introduction of the 50-year wind, for instance. It was in most parts of the world, that is, not in the United States. And then we came on in this century to performance-based codes. With these, we are using those ISO-TACs, ISO-PLEFs to allow us to say what it is that we want our structure to achieve. So in 1989, NIST and National Science Foundation were identifying performance assessment goals. And we still have 2022 risk and performance, which we're talking about. That was the Tay Bridge disaster, and the That was what it looked like before the collapse in 1879. SCE and SCI were producing. They had a task committee for performance-based design, and this is part of their mission statement. Although nearly all modern design specifications are targeted to achieve some level of performance, most structural design today is not performance-based. Rather, typical design procedures evaluate design acceptability through conformance to prescriptive criteria on materials, configuration, detailing, strength, and stiffness. That's a pretty damning statement. In other words, what that is saying is that despite the fact that we're still looking for um, acceptable performance, in practice, we're still looking at the criteria based on materials, configuration of a structure, detailing, strength, stiffness. Such criteria are deemed to result in structures capable of achieving acceptable performance without clearly defining the performance expectations. In other words, we need to measure the performance to be sure that we've actually achieved what we set out to do. Furthermore, the engineer using such prescriptive procedures does not explicitly verify the ability of the structure to achieve the desired performance. Well, actually, we have a way in which we can do it now. So take a step back for a moment, moving from a static assessment to those that affect risk. What we actually have here is force equals mass times acceleration. There we go, Isaac Newton. And we have the force and the building criteria here in an equation which allows us to calculate a number of things. So mass times acceleration, damping times velocity, stiffness times displacement. And if we modify this, we can actually say that the displacement is the force which will occur on the structure, and then some sort of representation of the structure. This part that's in here is actually looked at in this diagram here. So in other words, at zero frequency down here, we've got statics, and then up at the resonance, we've got dynamics, and we have a dynamic magnification factor, 1 upon 2 zeta. So zeta is that damping ratio that I was telling you about before. So in other words, what we do is in our codes of practice, we say what the maximum force should be for the once in 50-year event. And we will have a displacement which will be the stiffness elements in a structure, resonance frequency, damping in there as well. So in other words, we assume we know what the structure is going to do. We know what its stiffness is going to be. And if we take statics, we don't need to know any of this part about damping or the frequency of resonance at all. That's what we do. That's what we do with finite element programs as well. But why do we look to see what the displacement should be with a particular force? If we actually look at the displacement per unit force instead, then well, that becomes rather useful to us. So we did in the British government a lot of exercises of finding out what structures actually did. We shook this structure, this laboratory experiment with this vibrator system. We shook those 40 structures. So let's look at what the design is. We're saying we take a 2% chance per year. That's common, but you don't have to stick at 2%. Calculate the design event associated with this risk. Assemble the data about the design event for the chosen risk. For example, the 50-year wind. And then the designer needs to model their structure and test the model for the design event. In other words, the designer comes up with an architectural design, produces a model, mathematical, physical, or some other form of modeling. Then what we say is that that will test the response of the structure, and it will go up to an amplitude that we assume is okay. Why? Why do we not use Hooke's law and actually say, we need a displacement per unit force? Not a mnemonic which will tell us what the displacement is going to be, but the ratio of displacement per force will help us know where cracks are, what their importance is, that sort of thing. The problem in this is that this whole process is has a problem, and that is that neither the code committee nor the designer have all the information they need. Now, I'm speaking to you at the moment as a member of code committees in Japan, Australia, Brazil, and the United States. I'm actually currently on the ASCE committee looking at the assessment of existing structures right at the moment. What is structural integrity? Well, whether the building has the required capacity. So, in other words, capacity and demand. Demand will be what is coming in, what the designer has said is necessary. Capacity is what the building actually has. So, if you measure capacity upon demand, then you're well on the way to assessing the structure. ASC 11 and ASC 7 address requirements for, and Florida Building Code now has a requirement that if there is a 33% loss of horizontal capacity, then that is unacceptable. So, in other words, as somebody who is doing an inspection, you need to be able to assess how much loss there has been. Is that possible? Yes, it is possible. It is now. ASC 1199 is now MOP 158, and this actually has been there for 26 years. And it contains a lot of information written in a very unfamiliar sort of way. But that does allow you to do different types of in situ testing on a structure. So, for instance, we can do acoustic emission, sounding techniques, ultrasonics, ground penetrating radar, thermography, fiber optics, imagery, AR, VR imaging. So that's setting up a model which is virtual reality, which you can then compare with what the structure is actually doing. You can then go to dynamic analysis, integrated sensors, X-rays, core samples, in situ strength mechanism measurement, corrosion detection, ingress and transport, carbonation. And if you fix on dynamic analysis, and in situ strength measurement, then you can measure the holistic behavior, the actual response per unit force that occurs on a structure. So, how do we create a force? First thing to know about is that we don't need to. As long as we're looking at displacement per unit force, that's all we need to know. And that's by courtesy of Newton, Hooke, and Young. So if the wind is blowing, then we have a boundary layer, we have friction with the ground, and the boundary layer extends up a certain height, and the wind gets stronger as you go further. In fact, this will extend up probably somewhere around about 500 meters, maybe as much as 1,000 meters a kilometer. Now then, this combines wind and earthquakes. In fact, what we've got here is the displacement and the force along here. So this is, if you like, it's a stress strain diagram. But now we have as well a non-linear area. So we go outside the linear part of the area, and then we look at um, yielding or partial yielding of the structure until we get a fully yielded amount. This is the equation. Displacement per unit force is 1 upon 8 zeta F squared m pi squared. M is the modal mass of the structure. F is the fundamental sway frequency of the structure, and damping zeta is that value associated with this mode of vibration. So we can measure displacement per unit force, and only need to measure damping and frequency. Mass, well, it's something that we can't measure very easily, but if we measure the performance of a structure over what the expected response is, or the measured performance as the structure is put up new, then we can convert that to a risk for the structure, and the mass cancels out because the mass is going to be the same value in both of these parts. So once we've done that, then we can assess a number of things. Is the structure going to stay up with stronger winds? Is it going to stand up with bigger earthquakes? And we can assess it by a risk ratio, which is a ratio of its actual performance upon its demanded performance. Now, just to do an aside here, this is effectively a finite element model here. We have forces which we distribute over the structure, and we have equations that we've produced. Mass times acceleration plus stiffness times differential movement is force. So we've got F3 there, and that's what the equation is here. We've got stiffness values here, and we've got displacements, masses here. You know what's missing? Excuse me. Damping is missing. What we actually do with finite element programs is effectively using a quasi-static approach. And what we do after we've done that is to guess at what the damping value should be and assess what it might be under a large force. We are able to make damping measurements under earthquake loading, But when we do, when there's a big loading, then that tends to induce soil motion, ground motion as well. Whereas with wind, we generally don't have that occurring. But it's still the same structure. So if we use the wind, we can assess the structure. If we use an earthquake or wait for an earthquake to occur, then that's not so convenient. We have aerodynamic stabilities, instabilities. The Tacoma Narrows in 1940, and there is a bridge in Volgograd, 2010, where the same type of instability occurred in that bridge. So we don't learn from lessons. So what risk is acceptable? Well, we've said we'll accept 2% per year probability of a wind or an earthquake, which is unacceptable to us. And we use the statistical approach. So what's a force? We have the boundary layer with the wind. We have earthquake excitation coming through the ground, P waves and um, waves in the material of the ground. We also have water forces occurring. So we've got floods, we've got earthquakes, and we've got wind as the main items of forcing. We also have fire, of course, but I'm going to leave that to one side at the moment. How do we measure a force? We can use Newton's second law of motion, force equals mass times acceleration. In practice, what we do is we have a seismic mass, and we have coils on either side of that, so that if the mass tries to move, those coils will produce a signal which is sent into a feedback network and will then go to a little servo motor which will drive that mass back to its neutral position. So the force which is necessary to drive that is proportional to acceleration. Good old Newton's on our side once again. So in other words, that's quite easy. That's called a servo accelerometer. Producing a force, as I said, we had this vibrator system synchronized amongst them all to force buildings and other structures to vibrate. And in fact, here what we have is measured. This diagram here shows us this. If we stop the vibrators, then the structure will just lose its energy gradually. But as it does, then as the amplitude comes down, so does the damping. And the frequency changes slightly as well. Now, we were able, doing experiments like this, take the force, the frequency, the amplitude measured by our accelerometers, and the damping ratio measured off this kind of decay. So if we put these all back into the equation and use it to calculate what the mass of the structure is, then we find that even though frequency is changing, damping is changing, right the way through all these different amplitudes, then what we have is a pretty constant value for the mass of the structure, which is a pretty good indication that we're actually okay in saying, yep, we know that we're dealing with the linear elastic range, but in practice, we're not. We know linear elastic doesn't exist, but in fact, when you take these variations of frequency and damping together, then they compensate for each other where calculation of the mass of the structure is concerned. That's very reassuring. And there are common force generators, wind over roofs, if especially if the wind gets in underneath the roof where there's an open window. The wind gust will come in underneath and will blow the roof upwards. And there you see in this particular case, there was a roof missing. Tornadoes we get, there's pretty much nothing that you can do about designing to withstand a tornado. The forces there are extremely high. Flooding, of course, we've got quite a lot of that occurring at the moment, and the force due to water is significant, and we need to take care of it. This is the Alaska earthquake, which happened this last week, and just off the Aleutian Islands. So we've got all types going there. And this is a response due to an earthquake, which occurred, not the Alaskan one, but we took an excitation there, maximum acceleration 1.8 Gs. And so you can see the ambient excitation is small. Then as the earthquake comes through, then you see that little bit of aftershock as well. And what we do to produce our spectra is we take measurements and we look at what that is going to be, and then we try and find out what ground types there are, and we produce diagrams like this to say, this is our design spectrum. This is what we're going to give to the architects and the structural engineers to say, you've got a certain type of soil type, you're in a certain area, so this is what you have to design to. This is the so-called Van der Hoeven spectrum. This is frequency along here, and this is the force, the energy in the wind. Now, buildings occur in this area here, where we've got one cycle every 5 seconds, one cycle every 40 seconds up here. And our building stock occurs in this sort of area here. So the taller we get, the longer our bridges are, the lower the frequency until we come up to the peak here. There is a spectral gap, and there's then a semi-diurnal peak, and then a once every 4-day peak. Why? Semi-diurnal is because we have a difference between day and night, and once every 4 days, because on average, the time it takes a wind storm to pass a point on the Earth is 4 days. So there, that's the Van der Hoeven spectrum, and the measurements to produce this were made in Brooklyn, in New York. There's another force type, and that's where you have pile driving. This is a real case. So the piles were being driven, and we were measuring and looking at this and saying, no, it's a bit too large. 0.8 inches per second is too much. So we stopped, asked for a review, and we got together with the chap who was driving, and he reduced the force and reduced it down to below 0.5 inches per second. Here's a crack gauge, common sort of crack gauge. So you can see there is a crack. Actually, you can't quite see here very well, but there is a window there. And this is a stress razor here. So the crack is working its way out from that, and somebody has decided they want to have a crack gauge across there. What do you do when the crack is big enough? Do you say, we need to do something about that? Is it a problem to the building itself? No, especially if it's around a window or some sort of stress razor like that. So indications for a localized problem in the building, what to look for. So there are questions you should ask yourself. Is it in a load-bearing member? Is it confined to the surface? Do you need to test for the depth of the crack? Do you need to test the member which has a crack? Does it have implications for load carrying in a wider area, extending out into the whole structure itself? Does it indicate a holistic problem to the structure? This is a scanning electron microscope picture of a concrete sample. And what you have in this is a nascent crack. It's just forming. There are cracks that form in concrete all the time, and they will gradually get bigger and bigger as the structure dissipates energy. Now that's down on the micro level. This is 1 micron here. So obviously a crack as small as that is not a problem for a structure. How big does it have to get? Well, we have to look and see whether we've got a compromise to parts of the structure which are dictating load sharing throughout the structure. We also have human perception of vibration. My colleague Yuko Tamura produced this and put together a number of tests that people have done. So there is all these red dots are produced in laboratory tests, and that's the percentage of the population which could feel vibrations all the way down to 1%. So here we have, said to you, frequency of human beings are most accustomed with are in this range, 1 to 2 cycles per second. We did an induced vibration test in which we shook a building and had people do a number of tests in there. It's the only one that has ever been done anywhere in the world. And those numbers, 90%, 10%, and 2%, actually equate fairly well with the laboratory tests as well. So we've got an idea of what people will accept. Here, if we have a measurement which looks at the response of the entire structure, the holistic structure, then we know there's no elastic zone. It's an approximation. Ductility changes the system properties. It does not change physics. We are able to produce a random decrement signature, and this particular one shows us that damping is a fairly constant value, around 2% in this case, as the amplitude of response increases. So that allows us to calculate the risk ratio, the risk of what we have over what we are demanded. That also is a diagram of how damping occurs. If you have a stress strain diagram, then you have a circle, a stress strain excursion, and the width of this actually is an identification of the amount of energy lost in a complete cycle. In this particular case, there was a building in New York City, and there was a hut in front of this, and so the crack wasn't seen by people until the hut was taken away. We actually used 2 accelerometers, very expensive devices, $4,500 each, to measure what was happening in the crack. And that's probably the most expensive strain gauge that there's ever been in the world in that case. The crack itself was moving all the time. It was moving vertically, it was moving horizontally, and it was twisting as well. So we took all that. Crack gauge is quite a bit cheaper. And what we did find, if we looked at the damping, this is damping against amplitude. So before the crack was repaired, this was a characteristic. After the crack was repaired, we had a low amplitude plateau, a rise, and a high amplitude plateau. This actually agrees with the prognostication of what damping values ought to be if a structure does not have a problem with it. We should have a three-part curve. If there's something like this going on, there's a problem where energy is being dissipated. In this particular case, also in Manhattan, we did a finite element model to take a look at what was happening, and we were actually able to tell them that no, there wasn't a problem, despite the fact that it looked really bad. We were able to say that the majority of stiffness at this end of the structure was actually supporting the rest of the structure, and there was not a problem. And now these days, they didn't do a stop work; they just went on with it completely, and the building didn't fall down, and we saved them an awful lot of money. Additionally, no, I'm going to skip over that. So the approach for assessing a structure holistically is measure the performance at as an earlier time as possible. Secondly, compare the performance with that assumed in the design. After an event, wind, earthquake, subsidence waves, measure the performance again and compare the new performance with the baseline value and compare to the code requirements. The definitions of distress for humans, we have floors, bounce, the sway of buildings, and there's movement in bridges. If you sat in a vehicle on a bridge stationary, then you'll be aware of vibrations that can occur. Indications of damage: efflorescence, rusting of reinforcing, spalling of concrete, displacements of foundations. On the right upper side there, you see a displacement of a foundation, which is a rather extreme case. Differential settlement, large cracks. Now, the large cracks not only need to be surface width, which is significant, but also the depth as well. And if they are in structural members, then they're of more importance. Pooling of water in supposedly flat surfaces, leaking windows. If windows leak, then it's very likely that the building is swaying around, and the glass cannot do the same sort of thing as concrete will do. Foundation problems, you might see differential displacement there. So if you do, that can be an indication of a problem. And then aging brickwork. This week in New Orleans, this occurred, and the brickwork which was there was falling off, and so it was taken down. And apparently, the state of health of bricks throughout the United States is a particular problem. We have a very big problem. How do we inspect? To look. We need to do research. The research needs to come from a reputable source. So if it's generic, it needs to be peer reviewed. In other words, what force does the structure need to withstand? You need to take it from peer-reviewed journals or standards or codes of practice. If it comes from the internet, you should be very skeptical about it. You need to ask the right questions. Is this has this been updated? Does it tell you how the building is? Does it tell you about the repairs to the building that have occurred? Site information needs to come from a complete record. If the owners of the building management, doesn't have a complete record, then it can be a problem. We have a library which you may want to have a look at some stage. Certainly, we'll be lending this out to people at various stages. It will be a digital resource. A word of caution. The practitioners on one side of the field operating without an intimate knowledge of the other are inevitably courting a disaster that is avoidable. That is the design and the performance. The design groups, if they don't know what the real performance of a structure is, they won't be able to see whether their design is proper or not. That statement was actually in my PhD thesis back in 1981. It's available in the British Museum. Now, I'm going to go through this quickly because we're running out of time. But here are some towers in Florida. And those are the characteristics of the two structures. Here we have frequency and here we have damping. You can see the natural frequency of the north tower, east-west, is 0.425 hertz, and the south tower is 0.387 hertz. Damping, 0.387, the damping in the south tower, and 0.422 in the north tower. Now look at them. What's the difference? The only difference, they were built at the same time by the same group to the same design. The only thing that's different is this plinth here to allow a swimming pool. Conclusion that you can say is there is energy dissipated by this structure, the northern structure, into the plinth here. There isn't so much energy lost occurring in that southern tower. So there are a number of other differences as well, although they tend to follow a similar sort of route. This is from a much shorter building, and that's a view on the roof. There are excuse me. There are a number of attachments to the roof because they are a bigger mass compared to the mass of the building. They have more influence, and there's a spectrum of the east, west, and north, south. Now you see that in this particular case, the sensor placed here on a chimney is also picking up a lot of other structural responses of the chimney itself. The response is particular, but you have there same response in the two directions, so that must be a torsional response. And then we have the response. If we look down on the building, We we see it moving, swaying in the north-south direction. Torsion there. The again another torsional mode. The east-west direction. But now look at this measurement in the four corners of the roof. There is much more measurement. There's much more motion occurring in this corner of the building. So we look at the modal ratios and we can use that for going back to the building at a later stage and seeing if anything has changed. And if we look at a Randex signature, then we find that natural frequency and natural damping. So damping we've got somewhere around about 4%, and you would expect it to be similar to the frequency. Now we're seeing the frequency jumping about a lot though. That means that energy is being shared between two separate modes of vibration. And when we take this risk ratio, we can look at what the design wind load will tell us we expect a frequency to be and what we expect a damping ratio to be. And as a result, we can say that the risk ratio in this particular case was 1.38. So that is a return period 1,785 years. It's a logarithmic scale. So you can't just multiply by the value. Risk ratio though there is 1.38. Now I want to finish up by showing you a particular problem that occurred with one of those two towers that I've shown you before. In this particular case, at the 28th level, there is an excess of movement on that floor. That means that there is a reduction in stiffness at that area. How can a reduction of stiffness occur? Well, I'm not sure. But what it does tell you is concentrate your attention in this area because you're going to find something. You'll find stiffness elements which are cracked. You'll find errors of construction, various things like that. So this is the idea of actually pointing you in a direction to make your assessment in more detail. Why make the measurements? Well, I hope that I've persuaded you that there are lots of things that you can't see. If you make the measurements, especially if you make holistic measurements, then you'll be able to assess the building, the whole building better. So, additionally, if you're prepared to do it, code committees absolutely want this information. It can give reassurance to owners. Compare the response of the structure with code predictions. Perform a load test on the structure. Check the structures after an earthquake, thunder, hurricane, or flood, which tells us what the performance of the structure is going to be. And it also gives you a periodic health check. And it also tells you how much the structure is aging. So, in other words, it also defines exactly how long you need between assessment periods. We have new equipment coming along now. There are Wi-Fi connections, ultra low noise platforms available to us. It's possible to put in instruments onto a structure by drones. It's possible to use drones to take pictures of structures and to assess movement of the structure by that. Now here is something which is really disturbing because on this particular site there are 10 buildings all built to the same design. We measured all of them And then we assessed what the design wind would be, in fact, in meters per second, which would cause damage. In other words, what wind speed would take it outside the elastic range. Near the water, the values were around 40 meters per second. A little bit further away, 50 to 65, and further away still, 60 to 70 meters per second. So, in other words, there's some effect of degradation caused by a wet atmosphere, and that affected buildings closer to the water in that particular case. You would think if they were all the same, all built at the same time, they would all be in a similar state, but they're not. And so individual assessments are absolutely essential. Ladies and gentlemen, thank you very much indeed for your attention. And if there are any questions, I'll be happy to check them for you. Thank you. There's a question which has come up from John Contalefa. Ambient wind speed or individual speeds measured at each building? The measurement of wind speed is a difficult one, and you need to be 10 meters clear of a building. Otherwise, you get interference from the building. So, in other words, no, ambient wind speed would be best. Where? Well, it needs to be upstream of the buildings, but that's difficult by itself because if you have a mast which is 10 meters above level ground, then that takes a lot of setting up as well. The normal thing that we do is to take measurement from international airports. They are required by law to have a measurement which is in accordance with international standards. You'll find lots of places where people are putting wind speeds up for internet appraisal, and they don't say how high above ground they are, and you'll notice from what I showed with the boundary layer is that the wind speed varies considerably, just above ground level because of friction with the ground. So if you go up 10 meters, then you get to within 2 or 3% of the wind speed, which is further up. That is the gradient wind speed when it's further up. Now, there's another question though, and that is should you measure the mean wind speed or should you measure the gust wind speed? The most important thing for the integrity of a building is the gust, and that means that you must be well clear of obstructions so you can measure the gust. The ratio of mean wind speed to gust wind speed is variable depending on how long you measure for as well. So, in other words, there are equations which will tell you what you should expect the maximum gust wind speed to be during a period of measurement. Um, that doesn't help you very much, but nevertheless, what we're saying here is that the mean wind speed won't tell you everything. Mean wind speed will be good. The United States, just by the way, introduced the um, ISO DAX only in the year 2005. That was what was introduced in 2005. That was the wind speed, the risk of the wind speed of a certain velocity, which would occur in the United States. It was introduced in other places quite a bit before that, 20 years or so before that. And the United States was still working on a fastest mile occurrence up until that term. Okay, look, thank you very much indeed, ladies and gentlemen. It's been a pleasure, and it has come to an end, though. And thank you for your attendance. And the webinar will end now. Thank you very much.